Of the following populations, which ones are in Hardy-Weinberg equilibrium? Calculate P and Q for each, and for those that are not in equilibrium, calculate what the genotypic frequencies would be if the populations were to go through one generation of random mating. So in other words, calculate what the genotypic frequencies would be if they were to become in equilibrium. So let's just look at the first one here, population number 1. To calculate the P and Q, that means that basically what we have to do is we have to consider the gene pool and how many copies of each allele we have. So to do that, I'm just going to go ahead and assume that I have a population that's equal to 100 individuals. And if you consider that each individual has 2 alleles present because they're diploid, we are going to have 200 total alleles in that population. So keeping that in mind, if we think about the big A allele, and big A is going to be P here. If we think about the big A allele, you have basically 14% or 14 individuals of the 100, but of those 14 individuals, they have 2 copies of big A each. Okay, so that's my homozygous dominant ones. And then we also have some heterozygous individuals that have a copy of big A. And so if we're again considering that we have 100 individuals, you've got 36, because it's 36%, so 36 individuals, and they have 1 copy each of the big A. So if we solve this right here and we just add up really how many alleles we have in our gene pool of big A, we're going to get 64. So we have 64 total of big A. If we do the same thing for little a, we have some heterozygous ones, 36, that have 1 copy of little a, plus we have 50 individuals that, this is our little a's, and they got 2 copies each. So if we go through and we add all of this up, we have 136 copies of little a. So if we want to figure out the frequency of this, basically it's 64, and this is 64 out of 200 total alleles. And so if we do 64 divided by 200, we're going to get 0.32. That is going to be the frequency of P. And then if we look at this one out of 200 and we solve for it, going to actually, punch it into the calculator just to make sure our math is all correct here. So this is 0.68. And you can double check because remember that P plus Q, they're supposed to equal 1. So you could make sure that these together do sum up to 1. And they do in this case. So that's one way to just kind of double check our math and make sure that we have P and Q correct. So now if we want to know, answer the question, is the population in Hardy-Weinberg equilibrium? Well, the way that we would do that is we would go back to this equation here. And now that we know what P and Q is, we can look and we can say, okay, if I just get rid of this so it's out of the way. We say, okay, P is 0.32, and if I square that, what does that come out to be? So if we take 0.32 and we square it, that is equal to 0.102 if we just round it, or in other words, that's equal to 10.2%. And so that should be the frequency of big A. But if we look over here, the frequency of big A is actually 14%. So based on that, no, this population is not in Hardy-Weinberg equilibrium because our frequencies are not matching. However, if we wanted to come up then with what the frequencies would be if they were in Hardy-Weinberg equilibrium, big A, we've already said, should be 10.2%. If we do the same thing and solve for the other genotypes, 2PQ, this would be 2 times whatever P is, which is 0.32, times 0.68, which is our Q. And so if we multiply that, we get 0.435 43.5, or in other words, 43.5%. So that is our frequency of the heterozygous ones. And then if we look at our Q, this is Q squared, 0.68 squared. This is equal to 0.462 or 46.2%. And so that should be the frequency of little a, little a. Okay, so those are the frequencies of the genotypes if the population was to go through one generation of random mating and reestablish that equilibrium. If we go through and we start doing the same thing for population 2, remember that we're going to represent the capital letter allele, or capital B. That's going to represent P, and little b is going to represent Q. Okay, so if we want to calculate how many copies of the B allele we have in our population, again, we're assuming a population of 100 individuals, so I'm just going to say the 2.25% is equal to 2.25 individuals, and that is 2 alleles each for them, because again, that's my big B individuals. They've got 2 copies each. And then of my heterozygous ones, there are 25.5 individuals in my population that have that, and there is 1 copy of the B, capital B allele in them. So if we add all that up, we get 30 total big B alleles. If we do the same thing with little b, you've got the heterozygous ones, 25.5 of them, and they have 1 copy each. Plus we have the little b guys, and there is 72.25 individuals that have 2 alleles each. So if we do the same thing here and we add up what that comes out to be, we get 170. Keeping in mind that we have 200 total alleles, if we do 30 divided by 200, 30 divided by 200 is going to be equal to 0.15. So that is the frequency of capital B, so 0.15. And then we would do the same thing here, 170 divided by 200. This is going to be equal to 0.85. So that is the frequency of Q. Using that information, we now want to see, is this population actually in Hardy-Weinberg equilibrium? So again, using this equation, we know that the capital B, they would be equal to P squared, so they would be equal to 0.15 squared. Okay, so if we do 0.15 squared, that is equal to 2.25%. Okay, so that looks good. That's actually matching what the frequency is that we actually have of capital B. If we look at the heterozygous ones, remember that they are equal to 2 times P, which is 0.15, times Q, which is 0.85. So if we solve that, we get 25.5%. So again, that looks good. It's matching our population up here. And then if we just double check it with little b, the frequency of this would be Q squared, and so that's 0.85 squared. And so if you solve 0.85 squared, this is equal to 72.25%. So we can say that population 2, yes, it is actually in Hardy-Weinberg equilibrium, and over here, these would be the frequencies of the 2 alleles. For population number 3, we want to solve for capital C and lowercase c. That would be our P's and Q's. And so to look for the number of capital C's that we have, we know that 49 of the individuals in our population have a capital C. So that means that they've got 2 copies each of that particular allele. If we think about our heterozygous ones, there is 42 of those individuals and they have 1 copy each. So capital C, we're going to have 140 total alleles. And then if we look at lowercase c, we've got the heterozygous ones, and again there's 42 of those, and they've got 1 copy each. Plus we've got the little c guys, and there's 9 of them, and they have 2 copies each. So if we solve that, we've got 60 of little c's. And again, considering 200 total alleles, if we want to find the frequency of capital C, it's 140 divided by 200. So we have 0.7. So that would be the frequency of this allele. And then if we look at little c, it's going to be 60 divided by 200. This is equal to 0.3. So we've got our P and Q. Basically, again, I'll remind you that P is going to be the dominant allele, capital letter, and Q is going to represent the recessive or the lowercase letter. So now that we have those, if we just calculate what the frequency of the heterozygous dominant genotype should be, again, this would be, not Q, this is going to be equal to P squared. So we've got P squared, so if we solve that, we've got 0.7 squared. And so if we do 0.7 squared, that is equal to 49%. That looks good. If we look at the heterozygous, this is 2pq, would be what our heterozygous ones are equal to. So we've got 2 times p, which is 0.7 times 0.3. And so this, if we multiply this out, we're going to get 42%. And then if we look at little c, this is q squared. And so q squared is 0.3 squared. And 0.3 squared is equal to 9%. So since these frequencies that we're getting here match the frequencies up here, we can say that yes, that population 3 happens to be in Hardy-Weinberg equilibrium as well. For population 4, we have capital D and lowercase d. To calculate the number of capital D's that we have 16 individuals in our population of 100 that represent capital D. So they have 2 alleles each. Plus we have 36 individuals that represent the heterozygous genotype, so they have 1 allele each. So the total number of alleles that we have of capital D is going to be equal to 68. If we do the same thing for lowercase d, we've got the heterozygous ones, 36 of those that have 1 lowercase d, plus we've got the little d guys, and there's 48 of them, and they have 2 copies each. So if we look at that, we've got 132 little d's out of a total of 200. So if we look at the frequency of big D, it's 68 divided by 200. That is equal to 0.34. If we look at little d, 132 divided by 200, we get 0.66 here. Okay, so now we have our P and Q. Wrote that wrong, so let's change that to 0.34. Little d is 0.66. If we calculate the frequency, that should be capital D, remember that this is P squared, so this is 0.34 squared. So if we solve 0.34 squared, we get, if we just round it, we get 11.6%. So that doesn't look good. It doesn't match what we have over here in the population, okay, but that's what it should be. If we calculate for the heterozygous ones, it's 2pq, so 2 times p, which is 0.34, times q, which is 0.66. And so that would be get about 45% if we round it. And then if we look at little d, what we're going to get for that, that's q squared, so it's basically 0.66 squared. And that is equal to about 44%, again, if we round. We did have some rounding in there, which makes the numbers a little bit different. But if you did want to double check this, when you add these up, they should come to 100%. This is not going to equal exactly 100%, again, just because of the rounding differences that we did. But if you look at those numbers, they do not match the numbers that we have up here for the population 4. So no, this one is not in Hardy-Weinberg equilibrium at the moment, but if it were, these right here represent the frequencies of the different genotypes that we would see. For the last one here, capital E and lowercase e, we want the frequency of that. So if we look at how many capital E's we have in our population, we've got, of the homozygous dominant, we've got 34 individuals. They've got 2 copies of that allele each. Plus, if we look at the heterozygous ones, we've got 48 of those, and they have 1 copy of capital E each. So if we solve that, we get 116. So there's 116 copies of capital E. For lowercase e, we've got the heterozygous ones. So there are 48 of those. They have 1 copy each. Plus we have the homozygous recessive ones. There's 18 of those. They have 2 copies each. So if we look at that, we get 84 when we solve it. Out of the 200 alleles that we have, the frequency of capital E is going to be 116 divided by 200. That gives us 0.58. Okay, so we can write that over here. That would be P, essentially. And then if we looked at little e, it's 84 divided by 200, and that gives us 0.42. So that is our Q. I'll just remind you that when we look at P and Q, these should add up to 1, okay, and they do in this case, so that's always a good thing to do if you just want to double check your math. If we want to solve for the frequency of big E that we should have, that would be squaring the frequency of that allele. So we've got 0.58 squared. So if we do that, we get, I got 33.6%. I'm going to round that to 34%. If we look at the frequency of the heterozygous ones, we'd have 2 times the frequency of big E, which is 5.58, times the frequency of little e, which is 0.42. And so when we do that, that's going to round to pretty much 48%. And when we look at little e, we would take the frequency of that allele, which is 0.42, and we would square it. So if you do 0.42 squared, it's going to round to 18%. So note that these frequencies do match the frequencies that we see up here in the population. So this one also is going to be in Hardy-Weinberg equilibrium.